All right. Okay. Hello, everyone. I am not Eric Kubischta, but he's great at math. He's my friend that I do research with. I am Ian Teixeira. We do math and quantum together. Um, this talks about icosahedral quantum codes from twisted unitary T groups, which I'm sure is what all of you want to be hearing about today. She bombs got a big smile. All right. Okay, so it's based on the following papers: family of quantum codes with exotic transversal gates, which is our first PRL, and then this follow-up one, quantum codes from twisted unitary T groups, which was our second. Um, the first one was kind of just constructing a code that had an interesting property, and the second one was like some mathy generalization that is much less interesting to most folks, but I think is beautiful. Okay, so here's the setup. If you've ever done quantum error correction or any quantum at all, you know there's Hilbert spaces, usually multi-qubit Hilbert space, like 2 to the n. But you can also look at, say, a permutation invariant Hilbert space, which would be like size n plus 1 if you have all permutation invariant states of n qubits. So you have options in terms of your Hilbert space. And then C is the code subspace. For us, we usually just take a two-dimensional subspace, so just a single logical qubit. Although, of course, you can do more complicated things. We just heard a little bit about some of these crazy hyperbolic product codes that have like many, many logical qubits. And then in order to think about the logical gates on those, you have to think about much more complicated gates, which is tough, although it is something we're thinking about. So PC is the projector onto the code space, the orthogonal projector. And the first thing I'm going to say that's like kind of interesting here is this third bullet. You can define a logical error map where you take some error on the Hilbert space. So this is really any linear operator on the Hilbert space. And then you kind of project it down onto the code space by sandwiching it in between the code projector. This is a construction that you might have seen if you've ever heard of the Easton-Nil theorem. Anyone out there, Easton-Nil theorem? Yes, yeah, okay, some people. So yeah, the original proof in the PRL uses this kind of argument about projecting errors. So this is not an original idea. But the idea is it takes the error on the full logical space that could be like, x tensor 7, maybe, like x on every qubit or whatever. Or it could be x on the first qubit, z on the third qubit, any kind of error you have on the full Hilbert space, and then it sandwiches it between the projectors. So it gives you a sense of what is that physical error doing on your logical space. It could be mapping your logical space to something that's totally orthogonal to your logical space, in which case it's easily detectable. Or it could be doing something very, very nasty where it takes your logical space and it maps it right back onto your logical space, but kind of like flipped upside down or twisted or whatever. And that's a logical error. And we don't want that. So this is a nice way to think about how physical errors relate to logical errors mathematically. And the fourth bullet point is the first sort of novel thing here. This is what me and Eric do, is we take groups or representation theory and we kind of slap it onto quantum error correction. So our shtick is we always think about a quantum code as a representation of its transversal gate group. So we heard about transversal gates just in the previous talk, but yeah, like she said, the classic way to think about it is like a gate is transversal if you take single qubit gates acting on each of the physical qubits, and somehow that preserves the code space and implements some logical unitary. There are more general concepts of transversal, but that's sort of the one we'll be sticking with. And so the transversal gate group of a code is just, for our purposes, it's all the logical gates that can be implemented by tensor products of single qubit unitaries. And by Easton-Nil, that's the paper I was just talking about, that's always going to be a finite group. There are only finitely many logical operations that you can implement transversally. And it's like a famous result because everyone in like, I don't know, 1997 or whatever this stuff started was excited to be like, oh, quantum's going to be easy. We're going to do all of our operations fault tolerantly with transversal gates. It's going to be fantastic. And then they sort of found one code, another code, another code. None of them had a universal set of transversal gates. And at some point, people started proving that stabilizer codes cannot have a universal set of transversal gates. That's like a 2009 paper by some authors I can't remember. And then Easton-Nil a couple years later, I think it was 2011, proved that no quantum code at all could ever have a universal set of transversal gates. You always get finitely many of these. So that's some relevant background, but I figured these are originally QIP slides, so I think it's like they kind of went fast, so I should like give more background for a more diverse audience. Okay. So like here's our trick, right? This map, the logical map that takes us from the errors on the Hilbert space to the errors on the code space. If the code space is a representation, so it's preserved by the action of the transversal gate group G, then this map pi, the logical error map, will be G linear. So it's a homomorphism of like representations. And that's like a bunch of words, but the fact that we have that structure means that we can use Schur's lemma to learn a lot of things about which physical errors must be mapped to 0 in the logical space. So that means a physical error that is mapped to 0 in the logical space is always detectable, because that means it's taking a logical state, and it's mapping to that logical state to something that is totally orthogonal to the code space. So you can just measure and immediately know that this error has totally taken our data somewhere else, and therefore it's been corrupted. It doesn't do anything tricky, like pick up our logical state and kind of twist it around and put it back in a different place, which would be bad because that'd be corrupting our data. So we can use Schur's lemma, which is like the simplest first thing you ever learn in representation theory, in a clever way to learn things about our errors. That's sort of, if you remember nothing else, go home and Google Schur's lemma. It won't look that impressive, but you'll be like, huh, I guess this is useful. All right, that's the setup. And here's the picture. This is basically the whole presentation in a nutshell. It's a picture so nice that you'll see it twice. I'm going to bring up another slightly more detailed version later. So here's kind of the concept. We have the code subspace, which is tiny and sitting cutely inside the big physical Hilbert space. And then we have a group G, which is our transversal gate group. And G is a subgroup of, for simplicity, let's do SU2. Let's say everything qubits until the last slide when I'll say something about qubits, but everything qubits for now, everything qubits. So normally you think of a qubit being acted on by some 2x2 unitary. So that's a big group, right? I mean, that's like a Lie group with infinitely many elements. And there's a natural action of the 2x2 unitaries on, let's say, the Hilbert space of like 7 qubits by just taking some unitary, G, and you act on that 7-qubit Hilbert space by G tensor 7. You hit every single physical qubit with G. So this is some totally natural action of 2x2 unitaries on the Hilbert space. And if you have an action on a vector space, you can always lift that to an action on the space of operators on the vector space by conjugation. So I got a nod from Professor Bolon. He's like, that's true. I learned functional analysis from him. I learned many things about operators and all that. Okay, so if you have an action G tensor n on the vector space, then you can take some error. So this is just some linear operator on the physical Hilbert space, and you can act on that linear operator by conjugating. So G tensor n dagger times the operator, and then G tensor n on the right. So this gives us a natural action on the space of errors, and that's for any 2x2 unitary. And then you can take that representation and you can write it out as irreducible representations. That's what we always do in representation theory, and look at it as U2 representations. And this is all going to sound a little bit like nonsense to people who aren't familiar with representation theory, but this is what the talk is about. So it's sort of like is how it is. The thing that's kind of interesting and that's happening in the second column is that you start with a kind of coarse-grained decomposition of your error space into representations of U2. And then you pass to the transversal gate group, which is a much smaller finite group, and you get what's called branching. So some representation that might be irreducible for a big group, because the big group is strong and big and powerful and can move many different things to each other. For a much smaller group, so this finite group of transversal gates, that large representation will no longer be irreducible. It will decompose further in what's called branching. And so something, let's say like this 5-dimensional irreducible representation of weight 2 errors, which looks like, just to give you a little bit of sense of like how this kind of stuff works, right? So everyone's heard of like Tollies, right? So X, Y, Z, this is a 3-dimensional vector space of operators. So this transforms in like the adjoint representation or the 3-dimensional representation of SU2, because you could just conjugate these by, you conjugate x by some 2 by 2 unitary, you will get some other sum of like, you know, cxx plus cyy plus czz. So this space is like closed under conjugation. But you can also do something more interesting, which is if you move to 2 qubits, then you can get these more complicated error spaces. And it turns out that the space of all 2-qubit errors, so you have XYZ, tensor with XYZ, that's 9-dimensional. It decomposes into a 1-dimensional piece, a 3-dimensional piece, and a 5-dimensional piece. And just to give you a sense of like what this 5 is that I'm writing up here, I'm just going to go ahead and write out the actual. So this is like x minus yy. So there's some traceless diagonal pieces, so to speak. And then we're also going to have xy plus yx, xz plus zx, and then yz plus zy. So this may not be super meaningful to you, but the point is that this is like an actual concrete construction. These are actual 2-qubit errors or weight 2 errors. You can imagine tensoring on a bunch of identities. So you can make this a 7-qubit poly or linear combination of 7-qubit polys by tensoring on like 5 identities. And this is true on any subset of 2 qubits, that you get this nice decomposition. This is the bold 5 that you see up here. Then the bold 3 is, let's see, the anti-symmetric part. So it's stuff like this. xz minus cx and yz minus zy. So that's going to transform in like a 3-dimensional representation of SU2. And then you can count, that's 5 errors, 3 errors, that's 8 errors. So there should be 1 more. And that's like this totally kind of diagonal piece that's like xx plus yy plus zz. And you can check, you can conjugate this sum by literally any 2 by 2 matrix. Or, I mean, here it's the tensor action. So it's G tensor n. So G tensor 2, dagger, G tensor 3. You can conjugate this by any tensor product of G's, and you'll get back what you started with. So it actually commutes with G tensor 2 for any G. Anyway, that's just like a brief foray into representation theory, because I think not everyone here has like a super big representation theory background. Gives you a little bit of a sense of what we do. It's like a lot of big words, but also like just some very concrete calculations about how certain error spaces decompose in ways that are meaningful. And if you know certain things about the representation theory, then the kicker of this talk is that you can look at some subspaces and say, if my subspace transforms in this particular representation of this particular finite group, then I know for absolutely certain that if I act with any of these operators, these weight 2 ones, or any of these operators, or even like these weight 1 things, that they'll all take the code space to something that is totally orthogonal to the code space. So I know for absolutely certain that all of those errors will be detectable for any subspace that transforms in a certain representation. It'll be called pi2 bar of this exotic group called 2i. And this is sort of, I don't know, no one's ever really thought about it like that or had a result like that. It's a very strange result, because in some sense, you tend to pick your subspaces very carefully in the world of stabilizer codes. But here, you sort of get it all for free in this kind of strange case. And that's kind of what this talk is about. So what will end up happening is, because of Schur's lemma, these weight 1 errors will automatically go to 0 for a future case. Let's see. So, okay, the group that's the star of the show is this group called the binary icosahedral group. It is related to the rotational symmetries of an icosahedron. That's where it gets the name. So here's a beautiful pink icosahedron that Eric made. Eric made almost all the slides. He's much better at like overleaf and compiling and pictures and all this kind of business. And it's a very nice group. It's a perfect group for any mathematicians in the audience. It has this very pleasant character table with characters that go up to dimension 6. So characters correspond to representations. Not that easy to read a character table, but at least this first row is easy. This just says the size of the matrix. So this corresponds to a bunch of 1x1 matrices. This corresponds to a bunch of 2x2 matrices. This corresponds to a bunch of 3x3 matrices, etc. Okay. So the most obvious thing to do is to say, I'm interested in this group 2I. Why am I interested in it? Kind of a long story, but it turns out that there's three exceptional subgroups of SU2. One is related to the tetrahedron, one's related to the octahedron, and those are both related to Clifford, it turns out. So those, the 5-qubit, the 513, like whatever, nil code, or whoever did that, the little FLOM code, I think. The 513 code has a transversal gate group like the binary tetrahedral group, so that's kind of already been done. And then the Steen code, or any code you can think of that is Clifford transversal. The single qubit Clifford group is the binary octahedral group. So okay, that's also already been done. And I'm a mathematician, so I look at a list of 3 things, and 2 of them have been done, and I'm like, I want to do the third one. So no one had ever found a code that was binary icosahedral transversal. It turns out later that there's actually really cool things that this does, like that can help you as like a physicist do things faster and better. But at the time I got interested in this stuff, I was just like, yeah, it's math. So the sort of obvious representation to start with is pi2, which is just the one you get by, it's like the natural representation, physicists would say. It's just the one you get by looking at the standard 2I group of matrices. And then if you look at how the logical errors will act, so they'll act by conjugation, so it'll be lambda star times lambda, which it turns out branches as pi1, which is trivial errors. So these errors don't do anything. They just take a logical state exactly back to itself. And then pi3 is more or less going to act as logical x, logical y, logical z. So it's a 3-dimensional rep, right? The 3 denotes the degree. So it just looks like x, y, z in some basis. And that's our enemy, because that's going to corrupt our logical information. We must defeat pi3 somehow. And turns out to be a little bit tricky, because the weight 3 errors naturally, or the weight 1 errors naturally transform in pi3. And since the logical errors are also transforming in pi3, there's nothing to rule out that we can have a perfect isomorphism that takes all those weight 1 errors and maps them onto actual logical errors. But if we do something a little bit strange, if we instead choose a code that transforms in pi2 bar, which a priori looks very similar to pi2, but is like twisted by an outer automorphism, it's like, you can see it's basically just reorders the character table. This negative golden ratio goes to -1 over the golden ratio. Seems like it shouldn't be that different, but you like do some fancy math, and it turns out that lambda tensor lambda star, so the way that the logical errors transform, it transforms in pi3 bar. So now we're saying, okay, the logical errors will transform in pi3 bar. And so if we look at this picture again, something miraculous happens. And the miraculous thing that's happened is the weight 1 errors still transform in pi3 because that's controlled by SU2, the ambient group. That's controlled by kind of the fundamental representation. But because we've in some sense picked, I guess, the anti-fundamental representation for our code space to transform in, then the logical errors on our code space have to transform in pi3 bar, and it is impossible for pi3 to map to pi3 bar. That's the content of Schur's lemma. You can learn it on your own, but essentially what it means is that you can only map a representation, an irreducible representation, to a copy of itself. And if you try and map an irreducible representation to a different irreducible representation, you will just get the 0 map. Everything you started with will go to 0. So we have this kind of miraculous situation where all the weight 1 errors, they have to vanish on the code space. They cannot implement a logical error because we've picked this sort of anti-fundamental representation. And so if you find any pi2 sub-representation, this is giving you automatically a code that not only, in fact, is able to detect weight 1 errors, but can even detect weight 2 errors, because pi5 also is distinct from pi3 bar, and so also vanishes by Schur's lemma. And that is basically the point of the presentation. There's a lot more math in the end of this, but I think that it's better to try and like explain things that are more reasonable. So this was very exciting. We found that all lambda equals pi2 bar codes have distance 3 automatically. And turns out there's a lot of pi2 bar subspaces in this world, so you can find lots and lots and lots of codes, and they all work just sort of without any fiddling, without any fine tuning. This was the very first code we found. This is like a nice concrete form. It's just some code words, right? We've all seen code words. These Dickey states are just, so this is just the 0, 0, 0, 0, 0, 0, 0 state, just all zeros. D7-2 is just the 7-qubit state. That's the uniform superposition of all weight 2 stuff. So it's like 1, 1, and then 5 zeros, 1, 0, 1, and then 4 zeros, you know. So these are called Dickey states. They show up, they're permutation invariant n-qubit states. So this is a permutation invariant code. It was the very first one we found. This one transforms in pi2 bar, and so it has distance 3. But there are many, 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 many other codes that also transform in pi2 bar and all automatically have distance 3, although they're for larger numbers of qubits and they're less easy to write down. So this is really the content of our first PRL. The rest of the presentation is about the second PRL, but I don't think it's worth getting into unitary T designs and all that stuff. Just to sort of flash it across the screen. Oh yeah, and so why is it important? It turns out it has these optimal gate compilation properties. So not only do we find the codes kind of easily, kind of effortlessly in a way, but they actually have these very nice transversality properties that allow you to do sort of optimal gate compilation as described in this crazy math paper by Peter Sarnak. And so that is kind of exciting. They're even more efficient. They cover SU2 even faster with shorter number of gates than even Clifford plus T, which is kind of the standard set. So that was very cool. Not only had we found something that had mathematical interest, but it also has sort of physically compelling properties. And then, yeah, the rest of it is just like these like insane lists of symbols that are about how we generalized it. So we did a bunch of math and it was complicated. And then we did even more complicated math where we snuck in lambda. So this is like how the code transforms. So lambda is like pi2 bar in our case. And then we realized that if G is a lambda twisted unitary T group, then every subspace of the fundamental rep tensor n that transforms in lambda is a lambda dimensional code with distance at least T plus 1 and transversal gate group lambda G. So for us, that just means this thing about pi2 bar. Any pi2 bar subspace has distance at least 3 and transversal gate group 2i, which is exciting. And then the promised generalization of Q-trits. You can play this game with lots and lots of other groups as long as they have this lambda twisted unitary T group property. And one that's kind of interesting is there's a really big subgroup of SU3, and you can find interesting Q-trit codes this way. We found like a 4 Q-trit code this way. And everything's like a family, right? Because anytime you find a chi4 subrepresentation, it automatically has distance 2. So it sort of gives you a family of codes, not just one. Yeah.